Duffs Bridge and Marlee Bridge over Dingo Creek were handed to Greater Taree City Council in 1989. Both were single-lane Allen timber truss bridges. Timber trusses have become expensive and difficult to maintain due to the high-quality timbers and artisan labour required. These were Council's only two remaining timber truss structures. Marlee and Duffs bridges were completed in 1900 and 1926. The extent of celebrations for the original bridge openings highlighted the important role these bridges had for rural communities at the turn of the century. A reminder of the vital importance of these bridges was displayed when the 25-tonne load limits imposed in 2003 were reduced to 2 and 12 tonnes in 2008. Marlee load limit was raised from 2 to 8 tonnes after some costly timber rehabilitation works. Because of the restrictions to heavy vehicles, the local businesses, dairies, rural community groups and travellers on the popular tourist drive lobbied strongly for the bridge's upgrade. With 2 years of future bridge funding set aside and a $2.5 million grant, the council proposed to replace the bridges to provide the local community with reliable, safe and economically viable structures. Tenders were requested for the design, demolition and construction of 2 bridges on lengthy new alignments. Council's initial estimate was $5 million. The only conforming tender was over $9 million. A 30% contingency was required. Due to issues with tender scope, this resulted in an estimated contract cost of $12 million. In March 2011, all tenders were rejected. Council engaged GHD to project manage the investigation, design, demolition and construction of the 2 bridges. GHD outlined an ambitious 2-year program with a target completion date of April 2013 and a total estimated cost of $6.9 million. An options report and extensive site investigations were commenced. Staging was a critical consideration. The decision was to build Duffs first so Bulga Road could service the construction of Marlee instead of using the narrow, winding, unsealed detour for deliveries, cranes, precast items, concrete trucks and plant. Review of the options in May 2011 focused the project on 3 determining criteria: cost, functionality and traffic impacts. After assessing each option using weighted criteria and cost, 3-span, 2-lane bridges were preferred. Constructing Marlee on the existing alignment saved an estimated $1.4 million in approach roadwork. However, this required road closures. Therefore, to minimise the traffic impacts, Duffs was initially proposed on a new alignment immediately downstream from the existing bridge using Super T girders. In August 2011, Cardno was awarded the detailed design contract following an open tender. During the design phase, ongoing site investigations discovered an Indigenous artefact along the downstream alignment at Duffs. This had the potential to cause significant delays and additional costs. Instead, the project team used this as an opportunity to review the options and change the new alignment to the existing alignment. This minimised the disturbance of the riverbank and risk of impacting any other potential artefacts. A clever solution was required to keep this change from affecting the budget and program. Consequently, virtually identical bridge designs were developed for both bridges. This involved complex consideration of the different site constraints and road geometry. The pier alignment had to be designed to avoid the existing piers on both the 5- and 6-span bridges simultaneously. A variable-sized culvert span caters for the differing bridge lengths and the hydrology requirements. This clever solution made the design, demolition and construction of both bridges very similar, providing opportunities for innovation. Tenders were called and the contract was awarded to Delaney Civil in April and work commenced on site in June 2012. Regional Geotechnical Solutions recommended that permanently cased, large diameter board piles penetrating 3 metres into the rock as the preferred foundation method. The board piles also addressed the potential scour issues of the fast-flowing Dingo Creek. The two-pile piers were designed to be placed either side of the existing timber decks. This eliminated the need to pile through the existing deck. This also improved safety by reducing the time working around traffic. The steel-encased concrete piles were extended up to the headstock level. The 10-day closure periods and use of precast members minimised time in the waterway, reducing risk of exposure to flooding, as well as time spent working at heights. Site preparation included the crane pads, installing the temporary support structure, and delivery and storage of the precast components. The demolition options were assessed primarily on safety. When dealing with Allen timber trusses in poor condition, the truss's behaviour can be unpredictable. Demolishing the truss spans required complex analysis of different lifting options as truss elements change from tension to compression members and vice versa during the lifts. Chaining the end principles, propping and strapping all required engineering sign-off. Structures over 15 metres high require an unrestricted demolition licence from WorkCover. Duffs was over 16 metres high and a suitably licensed company undertook the demolition. Due to the site constraints, there was limited room for crane setup. The largest crane suitable for the site was a 500-tonne all-terrain crane. In the early hours of the morning, the bridge was closed to traffic and deck removal commenced. Each span was lifted, then lowered to be disassembled at ground level, improving safety by reducing the time spent working at heights. Due to the limited site area, the crane had to wait on standby for each span to be disassembled before it could lift the next span. Improvements were made at Marlee, which noticeably reduced the crane's standby time. An innovative temporary steel support structure was erected under the timber truss span to provide stability to the span and a sound platform to work from. The 500-tonne crane did not have the capacity to remove the truss span in one lift. Therefore, the span was cut and removed in two sections. The 500-tonne crane only needed to be configured to 350 tonnes. Construction on the existing alignment provided significant advantages by utilising the new piers to support the temporary steel structure. This innovative use of the permanent piers eliminated the need for temporary substructure supports, providing a cost benefit and minimising the safety risk of the supports being hit by machinery. Ingeniously, the new piers were designed to incorporate the temporary steelwork supports. This minimised the risk of damage when attaching and removing the temporary support structure. The virtually identical bridge designs was a clever solution and allowed the same steel support structure to be reused at Marlee. It also allowed similar demolition techniques to be used, although there are noticeable improvements between the Duffs and Marlee demolition. Using a 60-tonne crane, the end principals and the first diagonals were removed to gain access to the new piers, so the steel headstocks could be installed. Marlee was only 8 metres high, and Delaney gained a restricted licence and undertook the demolition themselves. The time-lapse footage of Duffs was used as a valuable learning tool for Delaney to manage their first major demolition project, and the results of the improved planning are visible. Demolished bridge members were removed, stacked, and transported out of the construction zone quickly, cleanly, and efficiently. The headstocks were installed at Duffs before the bridge closure, as the existing truss span was higher than the design level of the replacement bridge. At Marlee, this was not possible, as the truss deck needed to be removed to allow installation. The use of the steel headstocks was innovative, providing a cost-effective solution to span the distance between the two piles, whilst remaining light enough to be installed quickly compared to concrete. The timber trestles were carefully lowered and disassembled. The bridge closures required complex staging and intensive planning, including risk assessments and contingencies for plant, materials, personnel and weather. The 500-tonne crane had the reach to remove the entire truss span, including the steel support structure, in one lift. This required the crane to be configured to its full capacity, including the maxi-lift guide boom system. The timber truss span was removed from the bridge and then positioned across the river temporarily until the top compound area was cleared of precast planks. This shows the complexity of planning required for such a congested site and meant the truss dismantling could occur off the bridge closure's critical path. The key to using the existing alignments was to minimise the bridge closure's duration. The major benefit of using pre-stressed concrete planks with transverse post-tensioning bars is that it does not require an in-situ deck. Therefore, they are trafficable immediately, reducing the closure time significantly. The edge planks were lifted in with the scaffolding attached, providing instant protection for working at heights and safe access to install the transverse bars. This is a good example of safety in design and planning. Conduit was inserted into the transverse bar holes to ensure each plank was aligned correctly. A second 200-tonne crane was used from the opposite bank to lift in the far span. The planks were positioned into place using small hydraulic jacks against specially fabricated steel blocks. The blocks were located in the plank attachment holes already in the headstocks. At Marlee, the first lift worked the crane to near its maximum capacity, showing how critical craneage and access was at the congested sites. Time-lapse photography helped highlight critical path activities for the closures, and lessons learned from Duffs were then implemented into Marlee's closure. The site team showed excellent continuous improvement in planning and execution. Procedures were put in place to monitor the quality of the precast components. A trial assembly of the precast planks was undertaken in Brisbane prior to their delivery on site. This process proved invaluable in rectifying faults, including misaligned transverse bar holes, and preventing significant delays and additional costs during the closures. One improvement made at Marlee was having a scaffold crew continuously on site. As soon as the planks were lifted in, scaffold infills were immediately fitted, providing a safer work environment. Abutment headstocks and curtain walls were precast, so they could be installed quickly, reducing the bridge closure timeframe. Efficiency of precast production relies on the ability to implement a repeatable daily casting schedule. The design of the individual planks, with minor variations in length, skew or penetrations, is not efficient to precast manufacture and significantly increases the cost and delays in project delivery. Casting identical bridge planks double the casting efficiencies. Previously, there have been durability concerns regarding transversely stressed deck planks. Without an in-situ concrete deck in place, water could work its way through the grouted joints between the planks and corrode the transverse bars. The solution was to use a DiviDag DSI system, developed as a double corrosion protection thread bar for transverse post-tensioning. The system uses pre-grouted bars in a corrugated PVC sheath, overlaid with a smooth PVC skin the entire length of the bar. The pre-grouted transverse bars were slung into place and inserted as complete units. A 45mm thick bearing plate and nut were used for the anchorages. The planks were pulled together for grouting by applying a 100 kN load to the transverse bars. Cement grout was poured into the joints between the planks and left to cure for 18 hours. The transverse bars had to be completely released before the final tensioning to 350 kN could be achieved. Using this pre-grouted system eliminates the secondary grouting option normally required, whilst providing a simplified construction method and improved long-term corrosion protection. If future maintenance is required, the pre-grouted bars can easily be restressed or removed and replaced. Complexity of the site can be seen as multiple crews work on different tasks in such a small area with limited access. The quality site planning allowed construction to run smoothly. Now the top compound area was cleared of precast planks, the timber truss span was lifted from its temporary location across the creek. This completed the heavy lifts. At Marlee, the 500-tonne crane had been used to maximum efficiency, reducing the standby time significantly compared to Duffs demolition. The central sections of barrier rail were attached to the edge planks before installation. The remaining sections of barrier rail were pre-assembled and placed on the bridge before the scaffolding was removed. Adjustments for the barrier could be done easily as the end post anchorages were placed in the in-situ concrete curb infills. Drilling into the pre-stressed deck planks is not permitted, so all ferrules for the scaffolding and infill formwork were cast in place. They were then capped for corrosion protection so they can be used in the future if scaffolding is required again for maintenance. In November 2012, Duffs Bridge was open to traffic on the 7th day of the planned 10-day closure. In contrast, Marlee used the full 10 days of the closure to install the headstocks, asphalt the deck and install guardrail. The timber truss span was dismantled safely at ground level, reducing the time spent working at heights. This also allowed for the sound timbers to be reclaimed as part of Council's sustainable management plan to reuse in the remaining timber bridge assets. Another clever solution for this project was to design the temporary steel support structure so it can be used as an emergency bridge crossing or new bridge structure. This will benefit local communities recovering from future floods and is a sustainable reuse of material whilst also providing future cost savings to Council. At Marlee, the early part of the day was spent drying out the deck so a waterproof seal could be laid prior to the asphalting. Concurrent completion activities included removal of the scaffolding, removal of materials, site cleanup and re-establishing the embankments. During the concept stage, functionality considered design loadings, bridge widths, barrier performance, deck drainage and provision for utilities. These were assessed on the existing route standard instead of solely on the individual bridge site requirements. After assessing the width of the route, the bridge widths were increased from 1 to 2 lanes. This only increased the project cost by 5%. The design loadings of 44-tonne trucks and 68-tonne B doubles were also determined by assessment of the route. These key improvements provide increased safety benefits to the community and supports business growth in the area. Flexible joints, guardrail and signage were also installed to complete Marlee Bridge. Marlee's scheduled closure was delayed due to 2 flood events in early 2013. Good project management and use of innovative solutions minimised the time working in the waterway, mitigating the effects of the floods. Therefore, the finishing date and project cost was not affected. Marlee was opened within the planned 10-day closure in April 2013, achieving the target date set 2 years earlier during initial concept development. Council, in partnership with GHD, have achieved high-quality, innovative solutions normally only seen on much larger infrastructure projects. The solution was ingenious through the use of quality components constructed together in an original way, providing long-lasting community infrastructure at optimal value for money. The project team took the opportunities presented to make continuous improvements throughout the project. These project management skills are being implemented by Council for current bridge replacements. This project has been a huge success for Greater Taree City Council and the community they serve. In 1900, the official opening of Marlee Bridge was seen as quite an occasion. The local newspaper published a poem. They came from every farmstead, they came from Flatton Ridge, and even from the city to open Marlee Bridge.